All right, so we're going to get started with Unit 10 by talking about some basics of what are solutions, because that's what we're studying here in Unit 10. This is just going to cover page 1 of your packet. So as we get started, most of the solutions we're going to be making are going to be in water. So we need to understand a little bit about water before we get into the rest of these definitions and problems. So first off, remember, water is H2O, very important to know. And if we could draw that Lewis dot structure, a lot of what we're going to be doing with water and why it does what it does comes back to this structure. So jot that down for future reference. And then also back in Unit 5, when we learned to draw these structures, we learned that we can use those structures to find out the actual shape of the molecule in real life. So looking at that molecule, because there are 2 bonds and 2 lone pairs, 4 total groups, that's a tetrahedral electron geometry. But what we care about more is the real molecule in real life. What shape does it have? So those 2 bonds to the hydrogens are going to form the most of the shape. And if you think about 2 bonded hydrogens spreading out as far as possible, you might think that they would be nice and linear, kind of like I drew this structure here in that first space. But because of those lone pairs on the central atom, that actually causes the molecular geometry to be bent, which means we could draw that Lewis dot diagram in more of a bent shape, which is a little more realistic to what it looks like in real life. But it doesn't really matter in terms of the structure, but understanding that shape can help us understand some of the chemistry going on with water. Another thing we talked about back in Unit 5 was polarity of these molecules. And because we have those lone pairs on the central atom, the same thing that bends our molecule, that was automatically one of the 2 questions that could make us polar. And we'll review those ideas about how to tell if something's polar or nonpolar a little later in this unit. And then what type of intermolecular forces does it have? Well, because it has that OH bond, the hydrogen is directly connected to O, and that's what we called hydrogen bonding, which is the strongest of the intermolecular forces, which means water holds itself together very, very tightly to the other water molecules. So moving on, kind of coming to the chemistry of some of this water stuff. Why is the density of water in the liquid state more dense than the solid state? And I have a little picture of this off to the side in the slide and on your packet. As water, in liquid, these molecules can get closer. When it freezes into ice, they spread out and they make this kind of crystal lattice. And that's because of the polarity and hydrogen bonding we just talked about. As those molecules slow down, those hydrogen bonds are able to get the water molecules oriented in very specific places in order to maximize that hydrogen bonding. And because of that, they're going to actually spread out more and leave gaps between the molecules in order to get that arrangement that maximizes the hydrogen bonds between molecules. And then why is water called the universal solvent? It's because of that bent shape. Because of that bent shape, and makes us so polar, it causes that uneven distribution of electrons. This molecule is polar, but it's really polar. And so it can actually pull apart a lot of other polar molecules. Think of this like a magnet. Because water is such a strong magnet, it can pull apart basically any other magnet. And so water is really good at dissolving and pulling apart other compounds and incorporating them into their structures. So now we're going to talk about some definitions, and feel free to pause and write down as much as you need to here. I'm going to give you a basic explanation, but I don't need to read every word that's on the page necessarily. So, solutions are a special type of mixture. It's a word that we use for any kind of homogeneous mixture of 2 or more substances, which means there's 2 or more things together. They're mixed, but you can't tell the difference between them. They're homogeneous. They all look the same, even though there are different things there. And there are 2 parts to any solution. The solvent is the substance that dissolves the other stuff. The solute is the substance being dissolved. And if you're not sure what is a solvent or the solute when you're mixing something, then the solution is always going to be made of a majority solvent. So the short answer is it's whatever you have the most of in the solution. I know that seems weird, but like sugar can dissolve in water. So in that situation, if you put a teaspoon of sugar into water, the sugar is the solute, the water is the solvent. But if you put a drop of water into a whole bag of sugar, the molecules of sugar are the ones doing the work to incorporate that one drop of water. So because we have so much more sugar than water, then we would call sugar the solvent and water the solute. Now, that's not going to happen a whole lot here. Most of the time, water will be our solvent, but there will be some cases when it's not. And then alloys are just a special type of homogeneous mixture, a special type of solution where it's a solution of metals. So we've talked about that word before, just bringing it back where it's relevant. Now, electrolytes are going to be real important for this first day's activity that we're working with. Electrolytes, as the name kind of implies, are solutions that conduct electricity. So in order to conduct electricity, we have to have ions to carry those electrons through the solution. So there's kind of two things that you need in order to be an electrolyte. And make sure you write this down someplace where you have space. I think this area off to the left is probably the best place to squeeze this in. In order to be an electrolyte and have ions and moving and carrying electrons, it has to be ionic. So you're looking for something that has a metal and a non-metal in it. And it has to be dissolved in water for those ions to be able to move and carry electrons. So we'll practice that a little bit on that first day back. Now, not all electrolytes are the same. Some can carry more electrons better than others. So our weak electrolytes, have few ions and barely conduct electricity, whereas a strong electrolyte have many ions and conduct more electricity. Whereas a non-electrolyte does not conduct electricity. It might dissolve, it might not dissolve, but if it does not dissolve, if it's not ionic and it is not dissolved in water, then it is not an electrolyte. Now, last three definitions here. A colloid is not really a solution because we don't have solute particles completely dissolved and homogeneous. A colloid is a mixture of medium-sized particles that have mixed into some kind of, we can call it a solvent, but it's not really dissolving the particles. It's just helping them spread out and stay dispersed, but the Tyndall effect can still be observed. What is the Tyndall effect? Well, that's the scattering of light by small particles. Think of it like shining a laser beam through air or through a solution, a liquid. If you can see the beam, that means the light is being scattered. It's hitting all of the particles in that solution, and thus you're seeing that Tyndall effect. You're seeing the beam of the laser. If you shine it through something in the same laser, through a liquid, and you don't see the beam passing through the liquid, then there weren't particles big enough to scatter that light for it to hit and show that beam. So really what we're looking for, substances that do this Tyndall effect thing, stuff like milk, fog, Gatorade, smoke, Jell-O, and some aerosol sprays. So we'll try and give you an opportunity to test that in class. And then last word on the page, a suspension. Also not really a solution, but it's very similar to a solution. These are heterogeneous mixtures, which means that they're not homogeneous. They have different stuff, and you can kind of see the different stuff. But they kind of can seem like they're mixed together, but they're not dissolved, and they don't stay mixed. So think about like sandy water. If you shake that up really, really, really well, it might look just like muddy water. It might all look the same temporarily. But then if you let it sit, then the sand will settle and it does not stay looking the same. So suspensions tend to look homogeneous when you mix them, or at least more homogeneous, but then they become heterogeneous once you stop mixing them and moving them. So these are kind of mixtures that can separate themselves out. A lot like the pulpy orange juice. You can shake it up and it can get perfectly mixed. You pour yourself a cup of juice, drink it normally, but if you let it sit in the fridge for a couple of hours or even a couple of days, all that pulp will settle to the bottom. It does not stay suspended. It is definitely not dissolved. So that's it for your first podcast of this unit. Let me know if there's any questions that you have about any of these words, and we'll spend a little bit of time investigating them and moving forward in our packet next class.